Okay, guys, let me do a partial lecture today so we can get through some of the last material, and then I'll give you the rest of the time to work on the project. Okay, any questions about the project? Okay, all right, so I want to introduce control theory in this lecture, and then we'll cover real-time systems in the next lecture, and then that'll be all of the lecturing for the semester. All right, so as I mentioned in the beginning, this course is about cyber-physical systems, which is an embedded system that links sensing, computation, and control to the physical world, which is essentially another definition of a control system in general. So a control system is where you have a controller that is typically some kind of machine or computer that is able to manipulate the state of some physical object or system. And so the terminology here is the system, the physical system that it's manipulating the state of is called the plant. So the plant could be anything, could be an airplane, drone, robot, greenhouse, whatever you're trying to, cruise control system of a car, whatever you're trying to control is the plant. And so the assumption is that the controller has some kind of an input into the plant, usually through like an actuator of some kind. And then optionally, the plant the controller may also be able to read the state of the plant through measurements of sensors, right? So you've got like essentially an actuator is the connection from the controller to the plant, and the sensors are the connection or the signal coming from the plant back to the controller. And then the controller typically has some set point from a user that is the desired state of the plant. So this would be like, for example, the speed that you want your car to be at for the cruise control setting. And then the plant also has a secondary hidden input called disturbances. So for example, if your plant is a car, the disturbance might be unexpected, swerving in the road if you're trying to, stay in the middle of the road, for instance, right? If you have a self-driving car. And then if it's a drone, if your plant is a drone, a disturbance would be a gust of wind, right? So you want to be able to control the plant despite there being disturbances, okay? So there's some examples of control systems. So there's two types of control systems. There's open loop, which is where you basically just have the input from the controller into the plant, but you don't have a sensor coming back to the controller. So this is an open loop system. So examples of this, which drive me crazy, are toasters. So a toaster has a setting on it, a set point that's supposed to define how dark you want the toast. But the problem is that no toaster I've ever seen has any way to measure the darkness of the toast. So there's no feedback connection. So the toaster just basically has a timer that it uses. Yes?
Have you heard of the Sunbeam radiant control toaster?
No.
It's this thing from like the 1940s and 50s. They don't make it anymore for some reason, but it was this toaster from back then that would actually measure the temperature of the toast. And you could modify the set. It used this little like metallic strip to measure the temperature. And when the strip popped away, it would cause the toast to pop up.
Okay, so
it actually did measure the temperature right off the bread, but they stopped making them for some reason.
well, and that would be like, so that would be an example of a closed loop system where it has some kind of a sensor. Yeah, I don't think any modern toaster can do that. And the problem is that you have a disturbance in there, which is basically the type of bread you have. So different breads, like if you put sourdough, it takes forever for sourdough to toast. Whereas if you put white bread in there, it toasts really fast. Bagel, you put that in there and it takes a long time. So the problem is that the cook time is the input from the controller to the toaster, or maybe the temperature too. And there's just basically a table inside the controller that relates the input to how long you cook it, but there's no feedback connection. And the same thing happens with clothes dryers. At least maybe some of them have some kind of sensor now. But back when I was in college, it used to drive me crazy because I would put the clothes in there and then you'd have to pay, put coins in there. And the clothes would come out, they'd still be wet. So basically you would tell the controller there that you want your clothes to be dry, and they'd come out wet, meaning that there's no feedback connection. Now, a closed loop system is where you have some kind of feedback connection, or you have a sensor in the plant. And so if you had a toaster that had an optical sensor in there that could somehow withstand the heat inside the toaster, and it would look at the color of the toast, then that would be your feedback signal. And then the controller would then have an input that would be the difference between the set point or the desired color and the actual color. So generally you would subtract those two to get an error signal. And then that error signal would be the input to the controller. The error being, how far off the set point, or how far away from the set point the plant is actually at. And then that would dictate the input into the toaster, right? And that would be really great if something like that could exist. Okay, so the output from the controller into the plant are called a manipulated variable, and the signal from the plant back to the controller is called the process variable. So you have process variables, which are the sensed state of the plant, and the manipulated variables are what the controller is setting, right? And then, of course, you have these disturbances as well. Now, here's where this is where things get difficult. Because I mentioned that the plant is a physical system, it's in the real world, and everything in the physical world is dictated by differential equations. And they're continuous differential equations. The problem is that most controllers are computers and they're discrete. So you have to have a discrete system that talks to a continuous system. And that's where the problems start in control system design. Now there are actually there are ways to create a continuous controller. I've heard that there are greenhouses. In a greenhouse, you want to control the temperature inside the greenhouse very precisely. And the way that's done is through louvers. So the greenhouse on the roof has these louvers that open and shut. And if you want to increase the temperature inside the greenhouse, you shut the louvers. And if you want to decrease the temperature, you open them, right? So in a greenhouse, if you kind of close it off, it heats up, right, from the solar energy. And I've heard that there are louver designs for greenhouses that actually open and shut using thermal expansion of the louver itself. So as the louver itself gets hotter, the metal expands and it opens. And as it gets colder, the metal contracts and it closes. So that's a controller, but it's not a computer-based controller. And so it's a continuous controller, it's not discrete. But most controllers are discrete because they're CPUs that are running. So the problem is that when you want to design a control system, you have to have a model for the plant. And like I said, the model is generally going to be, if you're controlling any kind of physical system, it's going to be a differential equation. So I already said that. So the simplest way to do this is with an ordinary differential equation, which is what is an ordinary differential equation? That's when you have one independent variable, which is, in this case, time, right? So there's one independent variable. And furthermore, in control systems, it is generally the case that the ODEs are modeled as linear time invariant systems, LTI systems, which is a subset of ODEs, right? Not every ODE is a linear time invariant. What that means is that it's linear in the sense that each one of the state terms, and a state term is a function of time, right? So if it's a circuit, you might have current as a function of time or voltage as a function of time, right? In the case of a greenhouse, you have temperature, right, as a function of time. You can take that becomes a state variable. And then you can also take the derivative or any derivative of that term or any integral of that term, and you can multiply it by a constant, right? And that's what makes it linear, is that you only have constant multipliers of each state term or any derivative of a state term or any integral of a state term, right? So it's a little bit confusing because when you look at that, you're like, wait a second, you have an equation with an integral and you're calling it linear? That don't make any sense. That's not going to be linear. Not linear as I ever thought of linear. Yeah, well, they're linear differential equations. Linear ODEs are not the same thing as you normally think of as linear, as being a straight line, right? Okay. And then they're time invariant, and it's the fact that the coefficients of each state term being a constant makes them time invariant, which means that the coefficients don't change over time. They're fixed. Okay. Now, in reality, no system in the real world is linear. Typically, the common example you get is like a resistor, right? Resistors you think of as linear because they have they just have a fixed resistance, right? But that's a lie. They don't. The resistance of a resistor actually depends on their temperature. It's not linear. We just assume they're linear, but they're really not. And the same thing goes for like a simple mass spring system in physics where you have a spring. You have a spring, and springs are usually modeled as being linear, but they're not, because if you take a spring, and you stretch it out enough, it'll break, and then it's not linear. Or if you compress it all the way, it'll eventually stop compressing, and that's a nonlinearity in the spring. But within certain ranges of a spring, it exhibits, it's linear, right? And again, linear in the sense of linear ODEs, right? Make sense? Okay. Okay, so LTIs are known to have a frequency response, which is if you put a sinusoid into an LTI, and I'll talk about what that actually means to put something in, because technically an ODE doesn't have an input or an output, but we'll talk about how that's conceptualized. But if you have a system based on LTIs, and you put a sinusoidal input in, they can change the phase and the amplitude, but they don't change the frequency, right? So this is, you can build like a linear, filter, right? Where you can have it attenuate certain frequencies, and you can get a gain on certain frequencies, and you can have it change the phase. But the frequency, output frequency, will always be the same as the input frequency, right? And that's a restriction you have with designing those as LTIs. Okay, so as I mentioned, an ODE by itself is just an equation. It just relates two things. Like, for example, you could have a system, a very simple physics system, where you have the force with respect to time is the second derivative of the position, which is the acceleration, right? So this is dx squared over d squared t, right? Times the mass, right? So this is just the mass times the acceleration. And so you just have an equation, right? There's nothing about that equation that says, oh, there's an input or there's an output, right? And then you can also take this and you can look at it in the time, this is a time domain. You can also convert this to a Laplace domain, where instead of having it as a function of t, it's a function of s. So it's in the frequency domain. And in this case, you just take the second derivative and you just replace this with s squared, right? And the constants stay the same. So m stays the same. X here is, notice it's a capital X, whereas it was a lowercase x here. That's just because that's the convention when you go from time domain to frequency domain. And then s squared means the second derivative of that variable, right? And then again, f is also in the s domain. I'm not showing f. Technically, it's f of s, right? But this is kind of an abbreviated form. It makes sense? Okay. So, but the problem is, again, it's just saying force equals mass times acceleration. What's the input? What's the output? So the way that is conceptualized is through something called a transfer function. So in a transfer function is when typically you have it in you take the equation, you put it in the Laplace domain, and then you basically use some algebra in order to put it into a form where you have a ratio of two polynomials of s, and they're set up to where these are the ratio of the output variable divided by the input variable in the s domain, right? Now, if you wanted to switch the roles, like of the variables, if you like, so in this case, I've got two variables, force and position, right? So depending on which one you put in the numerator and which one you put in the denominator, and then you just use algebra to create a representation of that. That's called a transfer function. Okay, so let me show you an example. Oh yeah, well here actually I got one right here. So in this case, if f is my output, right? So I want to calculate the force, and my input is x, the position, right? Then I would just rewrite this as f over x. And then on the right-hand side of the equation, I just have ms squared. So I just took this, and I rewrote it to be, this. So I took f, see, I divided both sides of the equation by x. So I divided this side by x and this side by x. So I have f over x equals ms squared, right? So ms squared is called the transfer function in which I'm considering x to be my input and the force to be my output, right? And again, you could swap them if you want. You can have, depending on the system that you're designing, you could have maybe force as your input and the position is your output, right? Okay, so here's an example where we start out with a time domain ODE, which I just literally just made this up. This is not meant to represent any specific system. And I introduced these two variables. So I have u and y. Okay, so I've got two variables, and the reason there's two is because I'm assuming there's one input and one output. You could also have multiple inputs and multiple outputs, but if you do that, you're going to need multiple equations, right? And you end up with matrix form. You end up with a matrix-based transfer function. But in this case, I'm just saying one input and one output. And so if I want to create a transfer function, I'm going to first convert it to the S domain. So what that's going to do is that's just going to basically make the u and y capital letters, right? And then anywhere I have a derivative, that's going to multiply that variable by s. And anywhere there's a derivative, it's going to multiply by 1 over s, right? It's going to be, and then the constants stay the same. So in the S domain, I have capital U. Notice I left the S in here in this case. So you see this S in parentheses. Sometimes this is dropped, and it's just U, right? But then it's capitalized. So in this case, I kept the S. So U of S, capital U of S, right? Just like here I had U of T. So this guy is not, there's no derivative here, there's no integral, and there's no coefficient. So this just literally goes from U of T to U of S, right? And then Y of T is just Y of S. And derivative of Y with respect to time is S YS. And then the integral of Y with respect to time is S to the negative first power, right? 1 over S. And then that 6 is a coefficient, actually negative 6 is a coefficient, it just comes down, right? So that's just a real simple way you convert that to Laplace. And then if I want to create a transfer function where, let's say U is my input, and let's say Y is my output, and this is just, by the way, just what this means is that this is the model of the system, the dynamics of the system, but then based on how I'm using it, I have some input and some output, right? So the input is U, Y is the output, and then I want to create a ratio here of Y over U. I want to represent it as a ratio of Y over U. So what you end up having to do is you're taking all of the state variables and you're putting them on the left-hand side of the equation, right? And then on the right-hand side of the equation, you end up with just a ratio of two polynomials of S, right? So what you have is, so what do you have to do there? Well, you have to basically factor out, you're just doing algebra here, right? You're factoring out Y, you factor that out here, right? And then once you factor out Y, then you divide both sides. Actually, you divide both sides of the equation by U because you want Y on the numerator and U on the denominator. So you have to divide both sides by not Y, but U, and then divide both sides of the equation by this term, which is 1 plus S minus 6S to the negative first power. Make sense? Right? And so you end up with this as the transfer function. Okay? So again, left-hand side is your state variable, ratio of two state variables. Right-hand side is also a ratio, but it's just a ratio of two polynomials of S, right? That's the form that's typically used. Now, oh, by the way, usually this would be further modified so we wouldn't have any negative exponents of S. So typically this would also be, this side would be multiplied by S over S. So you'd have S over here in the numerator, and then the denominator would have an S squared, an S, and a minus 6, right? But I didn't finish it, but that's typically the next step, right? You want to get into that. That's the canonical form. Okay, so why do we use transfer functions? Because transfer functions have this cool property where you can compose them, meaning you can interconnect them by just multiplying them, right? So the reason why they use that, that ratio form is because if I have, say, two transfer functions, and I take one transfer function and I want to connect it to the other in series, right? So the output of this guy is going to feed into the input of this one. You perform a what's known as a convolution operation, where in the S domain, in the frequency domain, you just need to multiply the two transfer functions together. So if I take y over u and I multiply it by g over y, what ends up happening is that y cancels out, right? Make sense, right? So then I end up with g, which is the output of the second transfer function, over u, which is the input to the first transfer function. So what ends up happening is this intermediate value in between these two transfer functions basically goes away. It gets, absorbed into just an equivalent transfer function, right? So you've got, you end up with this where you just have g over u, right? Now, you might be wondering, well, what is the point of that? Why would you ever need to do that? Well, this is basically what Simulink does in MATLAB. If you ever heard of Simulink, right? The idea is that you take these transfer functions and you connect them together. And in this case, you're basically, what you've done is created an open loop controller here where y is, and again, but this is y of s. And also, the notation is a little weird. There's a lot of shorthand in the notation. So as I mentioned, these are all S-domain functions, ODEs, LTIs, I should say, linear time invariant systems. And the block name is y. It's called y because its output is y, right? But in reality, this should be y over u, right? But they don't use y over, well, I have y over u here, but usually when you see this, you'll just see it abbreviated as y, and you don't see the s, but it's really y of s over u of s, right? This is all shorthand, right? So here we've got an open loop transfer function where you've got y is the controller and g is the plant, right? Make sense? Now, the problem is that LTIs are continuous, and the controller is never going to be continuous. So technically, this still isn't quite an accurate representation of the system. We've got the plant and the controller are both ODEs, when in reality, controllers are not ODEs. But this is just a kind of a first step. Okay, so control systems have several properties that you're trying to achieve when you design them. The most basic of which is called stability. You want it to be stable, meaning that if you give it a bounded input, and by the way, what is the input here? The input is the set point, right? So the user, the input, the top level input is basically like the cruise control, setting on your car, right? And then the output here is the state of the plant, right? Now, if you have an open loop control system, it's just the two transfer functions convolved, right? Multiply together. If it's a closed loop transfer function, you also will have this internal connection, which I'll talk about how to realize that mathematically. But from the perspective of the whole system, controller plus plant, you just have one input, one output here, right? And you want that system to be stable. You want it to be bounded input, bounded output, stable. What you don't want is you don't want you to set the cruise control on your car, and then the car tries to get to that speed. So it speeds up, but then it overshoots, and then it slows down, and then it overshoots, and then it speeds up, and it overshoots, and then it slows down. And every time it does this oscillation, it keeps going wider and wider and wider ad infinitum, right? That would be an unstable system. And it's possible, depending on how the cruise control system is designed, for that to happen. It could very easily do that, because if you don't have the control system tuned properly, it'll oscillate in a way where the oscillations get larger and larger, and that would be an unstable system, right? Now the problem is that, you know, the plant itself is usually unstable. So, like, for example, even in a car, assuming you realize it as a linear system. So if you think of your car, if you just apply a constant acceleration and you assume there's no non-linearities, then it'll just accelerate infinitely, right? It'll never stop. That's unstable. That's an unstable transfer function. So the idea is that when you combine that unstable plant with a specific type of controller, then the system as a whole becomes BIBO, bounded input, bounded output stable. So the question is, how do I know if a system is stable, or any transfer function? How do you know if it's stable? Well, as far as I know, there's 3 ways to do it. There's one way to do it is to look at the impulse response. So the problem is that, let me back up here a second. So generally, if you have a transfer function, it may be stable for some frequency ranges, but not for all, right? So what you don't want to do is design a system and then give it a sinusoid, right? And then look and see, well, it's stable, right? Because you don't know, some frequencies, some input frequencies may make it unstable, right? So a better way to do it is to give it an impulse or a step function, which is where you go from 0 to 1 instantaneously. Because those functions contain an infinite set of frequencies in them, right? So in other words, if you wanted to create a step function by adding together sine waves, you have to add together an infinite number of sine waves to get that step function. Although the amplitude, as you go higher frequencies, the amplitude, you know, goes down. But it's still, it has infinite bandwidth, you know, that step function. And an impulse is kind of like a step function, except an impulse is even more generic, where it says, at time 0, I want to put infinity in. And then any other time aside from time 0 is a 0 input. That's called an impulse, right? And again, just like a step function, an impulse contains every possible frequency. And so if you hit a transfer function with an impulse and it's stable, it doesn't blow up, then you know that that transfer function is stable. There is another way that you can do it, though. If you have the S domain transfer function, all you have to do is find the poles. Did you guys ever cover poles before in circuits in 222? So a pole is, I mentioned that the transfer function usually is in this form here, right? It's a ratio of polynomials. Well, there are values of S that will make the denominator 0, right? Where you'll divide by 0. And for every possible value of S where the denominator is 0, that's a pole, right? Likewise, there's zeros where every value of S where it gives you a 0 in the numerator. But in the case of checking for stability, you're looking for poles. And so, the S value, by the way, is a complex number. And so if all the poles have a real part of the complex number, again, when I say poles, what I mean, if you have a polynomial, the number of roots of the polynomial depends on the degree of the polynomial. So if it's a second degree polynomial, there's 2 roots, right? Up to 2 roots, right? And so those roots are going to be, where the polynomial is 0. And if you're looking at the denominator part of the transfer function, that's also going to be the poles, right? Because if the denominator is 0, that's a pole. So if you find the poles, And for each pole, the real part is negative. That means that it's stable. Make sense? So I'll show you an example of that in a second. And then the other thing you could try is you can simulate it in MATLAB, and Simulink, and any other kind of simulator. Now, what's a simulator? What do I mean by simulator? So if you're taking a differential equation, an ODE, and you simulate it, you're basically, what you're doing is you're using a numerical integrator, right? You're running a numerical integrator, meaning that you're essentially tracking the value of that ODE over time, right? And that's what Simulink is doing for you. You can set up these transfer functions, and you just hit simulate, and you can actually plot the signals in the time domain, right? So in this case, this impulse response is, can be done mathematically. This can be done mathematically, or this you have to use a numerical method, like a software package that can do, right? And again, you could simulate it with an impulse or a step, and you can see what happens, right? A lot of people just do this. You know, they just use software to figure this out. And there may be other ways, but these are the three ways that I know of to know if the system is stable. Okay, so as I mentioned, how do you look at the impulse response and the step response mathematically? Well, in the S domain, the impulse is 1, right? So if you have an impulse in the S domain, it's just 1 in the S domain, right? This is also called the Dirac delta function, you know, and it looks like this, right? 1. 1 at 0, 0 everywhere else, right? A step, on the other hand, a step function looks like this, right? It's 0 at every value less than 0 and 1 at every value greater than or equals 0. The S domain representation of a step function is 1 over S. Okay? So what that means is that you can feed in a impulse into an existing transfer function by just multiplying it by 1, which basically means you don't have to do anything. You just look at, if you look at the regular transfer function, that is already the impulse response, right? On the other hand, if you want to look at the step, you can multiply it by 1 over S, but why would you do that if the impulse is just as good, right? So generally, that's why it's the impulse response is typically what you do. So here's an example of that. So we have an example transfer function here. This is the one I used before, right? So this is output is Y, input is U, and the transfer function is 1 over 1 plus S minus 6S minus 1. Okay, and as I mentioned, that typically you would put it into this form, right? Because it's easier to find the roots if it's in this form, right? Right? Okay, and then to find the roots, I can factor this polynomial. So S squared plus S minus 6 is S plus 3 times S minus 2, right? So already you can see what the roots are here of this. Its roots are -3 and +2. So if S is -3 or +2, that will make the denominator here 0, and that will be the poles of the transfer function, right? And in this case, even though S is a complex number, there's no imaginary part in this example, right? There's only a real part. But the problem is one of the real roots is -3, and the other one is +2, which means this is not a stable function, right? So, yeah, so generally, there's this thing called a pole and zero chart. So you'll often see where they'll take the imaginary part of the number, and that's the y-axis, and the x-axis is the real part, and then the poles are you put x, and the zeros you put a little o, right? You put x's and o's. But in our case, we only care about the x's. We only care about the poles. So notice that one of these x's is on what they call the left-hand plane, right? It's to the left of the vertical axis. And the other one's on the right-hand plane, which means it's not stable. So what ends up happening is, well, there's a couple things we can do. What do we do from this point? How do we know it's not stable? So one option is to calculate the impulse response, but do it, we want to see it in the time domain. The impulse, the response is going to be in the time domain. We want to see what happens when we hit this with an impulse, right? So in order to do this, we have to take this transfer function, multiply it by 1, which does nothing, but then calculate the inverse Laplace transform. We got to get this back in the time domain, right? And so if we take this is the impulse response, and we take the impulse response and convert it to the time domain, what we should get is a time domain plot where we have time, where we have the value of coming out versus time, right? All right, so how do you do the inverse Laplace transform? It's well, it's kind of tricky. So as far as I know, the only way to do it really is to use a table. You basically have to use a table where you match forms, equation forms, to the corresponding time domain. I don't know of any way to do this without using a table, right? So if you look at the table, so typically Laplace transforms, or you'll see a table, and there is a very common form is 1 over s minus a in the s domain is equivalent in the time domain is e raised to the at power. It's an exponential, right? Now they're not all exponentials, but if it's in this form, it's an exponential. You with me? Okay? So, but the problem is we don't have it in that form. We have this. We don't have it in 1 over s minus a. We have it in this form. So what do? Well, you have to get it into this form first. You have to do some, it's like, you have to do algebra, right? In S-domain algebra, right? So what we need to do here is we need to take this expression and decompose it into two pieces, right? A over s plus 3 plus b over s minus 2. And then we can take each one of these sides and do the inverse Laplace. And again, the reason for this is because this just happens to match what's in the inverse Laplace table, right, is this form. So we have to get it into this form, meaning we have to split this into these two parts, right? Make sense? So in other words, we have to solve for a and b. We don't know what a and b are. But there's a problem here. Normally, if you're solving for variables, don't you have to have two? If you have two unknowns, you have to have two equations. But we have two unknowns and one equation. So it's impossible to solve this, right? Like it's an underdetermined system, right, of equations, right? Well, it turns out that you can solve it sometimes. You can use this magic trick, right? So the magic trick is first of all, you find the least common denominator of these two sides. Least common denominators. S plus 3 times s minus 2, which was the same denominator we had before, right? But in this case, we say, well, if it's in this form, and I convert it into this form, I would have to take the a and multiply it by s minus 2 in order to get it to have a denominator of s plus 3 times s minus 2, right? You guys with me? Right? And likewise, b would have to be multiplied by s times 3 in order for it to have that same denominator, at which point they have a common denominator, right? You guys with me? Right? So, but I still have just one equation and two unknowns, right? But now I can multiply both sides of the equation by that denominator, because now they both have the same denominator, right? So if I multiply everything by s plus 3 times s minus 2, then I end up with just s, just the numerator here, equivalent to the numerator here, right? Because both sides have the same denominator, right? Okay? You see where I'm going with this? Okay? So then you still have one equation and two unknowns, right? So how do you figure this out? Well, let's just assume, let's pretend that s happens to equal 2. If s were to equal 2, then s minus 2 would be 0, and it would knock out a, right? And then I would be left with one equation with one unknown, b, right? Make sense? And then I could solve for b. Or if we pretend that s is negative 3, that would knock out b, and I would just be left with a, right? So that's what I'll do. I'll set s to be 2, in which case I'll have an equation that's 2 equals b times 2 plus 3 is 5, right? So s equals b, 5b, right? So then I have, and then I can also set s to negative 3 and do the same thing and solve for a, right? Now the problem, you might say, well, how is that possible? I mean, everyone knows that if you have two unknowns, you have to have two equations, right? Well, it turns out that this is only possible because a and b are unique, right? This wouldn't work if, you know, if the roots, if you're the same root, right? We have two different roots. But anyway, so now I can solve here for the, if I plug, so a ends up being, what is it, 3/5, and b ends up being 2/5. Make sense? So then I can just put those values back in for a and b, and now I have an equation here that I can take the inverse Laplace transform, because all I have to do is now look at these two terms and do the inverse Laplace transform on both individually, right? And then what you end up with is, you end up with this a value. A, it's 1 over s minus a. So this numerator becomes just the coefficient, right? And then this 3 becomes the coefficient for the exponent, right? So you end up with the inverse Laplace transform of this ends up being 3/5 e negative 3t to the negative 3t. Again, the 3 comes from here, right? So this is negative 3, is a is negative 3, right? Because remember, it was 1 over s minus a. And then, what was the other term? 0.4, 2/5. 2/5 e to the 2t, right? So the inverse Laplace transform is this. These are also called the eigenfunctions. And then if you plot this, you end up with, what this is this is the impulse response, but it's in the time domain. So if the input to this were an impulse, like a, you know, you hit it, the output goes up infinitely, right? It's unbounded, right? That makes sense? Now you might say, well, yeah, aren't they just all going to look like that though? You're just talking, it's just an exponential. Yeah, but you can see when it happens at 8 seconds, right? Basically at 8 seconds is when you get the elbow of that curve and it shoots up, right? Okay. Now in Simulink, you can do this. So now in this case, I didn't use the impulse. I actually used the step function instead in Simulink. So I gave it a step function, because in Simulink, I don't think you can do an impulse. Or I never figure out how to give it an impulse in Simulink. So in Simulink, you can give it an impulse, step. This is a step function. And then you can look at the corresponding output, right? And you can see in this case, when you give it a step function, it starts doing this type of oscillation I described if you had a malfunctioning cruise control in your car that keeps kind of oscillating back and forth, right? And then you can also give it a, instead of a step or an impulse, you can give it a single frequency. But like I said, you could have certain frequencies that are fine, even with this function, right? The reason we use a step or an impulse is because all the frequencies are there. But if I give it this frequency, which is sine 2t, which is a, and again, by the way, in Simulink, everything is, you put everything in the time domain, right? In terms of like the input, like the input signal, right? And then the transfer functions you can specify in the S domain. And then you simulate it and you get a time domain output. So in this case, I'm going to put in a sinusoid at 2 radians per second. And then, you can see what it does. It still blows up. It doesn't like that frequency, right? Okay, so likewise, let's just take another quick example here where let's assume that I had a stable one, right? So here's a stable example. All I did was I just artificially set the transfer function so the two poles were negative, right? I just changed the sign of one of the poles, and then that would be a stable function. And then I did the inverse Laplace transform, and this time I got, again, an exponential function, except this time it's a sum of two exponential functions, but the exponents are negative. They both have negative coefficients. So what ends up happening is if you hit this one with an impulse, it's kind of funny, like it starts out at 1 when you give it an impulse. So you give it an impulse, and the output is immediately goes up to 1, which is the impulse is 1. But then it comes down, it overshoots 0, and then it comes back up, and then it stabilizes here at about 0, right? So this one is stable. So no matter what input I give this thing, the output will be bounded, right? So here's an example. This is in MATLAB now. I went into MATLAB and I gave it a step input, and you can see what it did is, and again, this is a step. The one I showed before was an impulse. This is the step response. The step response is it goes up, and then it comes down like this and kind of just stabilizes, right? Okay. And then in this case, I'll give it a sinusoid instead of a step. Now check this out. You'll notice here that the input sinusoid has an amplitude of 1 and a phase of 0, right? Because the sine wave, that's a 0 phase, right? But over here, the amplitude is like 0.2. So this one is attenuating the input signal. And it seems like it's out of phase. See that? It looks like it's out of phase because it's got a weird starting point here, right? So it's changed the phase and the amplitude. Okay, so let's so how do you apply this to an actual system? Here's a real simple example. So let's say that I'm designing a robot that it's got a finger, and I want it to move a coin across the floor to a set point, right? So in other words, I want a robotic finger to say, move that quarter 1 inch, right? So, so the first thing you'd want to do is define a model for the plant. The plant is the physical system of the quarter, right, sliding across the floor. So in this case, now by the way, the notation also gets weird with this stuff. So I just found this out this semester actually. When it comes to calculus notation, there's actually 3 notations. So if you've got a derivative of y with respect to x, and you say dy over dx, that's called Leibniz notation. You ever hear that? That's the Leibniz. But on the other hand, you can say y prime of x, right? It turns out that's the Lagrange notation, right? Or you can just say y dot. And I never even seen this notation until recently. This is Newton's notation. This is what Newton used. Newton didn't use dy dx. He used y dot. Of course, I would argue, how do you know what variable is this taking a derivative with respect to? That's kind of lost there, but apparently Newton wasn't concerned. He just said y dot, right? Okay, so you see all 3 notations when you deal with these. So in this case, I'm going to switch and use the Newton notation. So in the Newton notation, if I have, let's say U is the force, say the robot is capable of exerting a force on the coin, right? That's what I'm going to consider the input to the system. Even though, again, the system itself does not inherently have inputs and outputs. It's just an equation. But the robot is capable of taking a force as an input. And then X is going to be, sorry, Y rather. Y is where the coin ends up. That's the position of the coin. So you can define the system as being the force is mass times acceleration, right? So acceleration is going to be y dot dot, second derivative. So mass times y dot dot, right, is going to be equal to the force that I put on the coin. So the total force is going to be the force I put on the coin minus B, which is the coefficient of friction. So the coin, as you drag it across the floor is going to resist the movement. But it's going to resist it as a function of the velocity, which is y dot, right? So the first derivative of y is how fast the coin is moving. And the faster that coin's moving, the more of a resistance I'll get due to the drag or the friction, right? So it's u input force minus the friction force is equal to the overall force, right? Make sense? Okay, so then in this case, I'm going to take the Laplace transform, so I'm going to capitalize u and y. Notice that this is time domain, this is frequency domain. The y dot goes away, the dot goes away and is replaced by s. And the dot dot goes away and is replaced by s squared, second derivative, right? Okay, so now I've got u minus bsy equals ms squared y, and all you have to do is calculate the transfer function, where again, y is the output, that's where the coin's at, and u is the force that the robot's putting into it, right? So it's y over u. And y over u ends up becoming a transfer function of 1 over m divided by s times s plus b over m. Make sense? So is that a stable or unstable transfer function? Well, it's unstable because there's two roots. One root, or one, I should say pole, there's two roots of the denominator, sorry, which are the poles. One pole is s equals 0, and the other pole is s equals negative b over m. So the s equals 0, that's a problem, because that's on the vertical axis, but that's not the left-hand plane. That means it's unstable, right? So what does that mean? Well, what that means is that if I give it an impulse, what is the impulse? The impulse would be the robot going from 0 force to 1 force instantaneously, which would shoot it across the universe, right? Basically, right? And so that's how that manifests. Oh, sorry. Okay, yeah, anyway. So if you go into MATLAB and you simulate that, actually what you'll see in MATLAB is, in this case, it's not the impulse, it's the step. So this is saying robot 0, robot gives it 1 Newton, but that 1 Newton just stays the same. And then the position of the coin will just, shoot away, right? Okay, so here's another example. This one's a little simpler, actually. This is a spring mass system. So let's say I have a mass that is connected to a ceiling or something, some kind of anchored point, right? And it's connected through a spring, right? Now this one is, you're going to have a variable called x, which is the position of this mass. And u is the force on it, right? So, so this is actually a little simpler. Well, it's kind of similar, actually. It's, in this case, you've got, again, mx, so mass times acceleration here is equal to, this is like the equivalent to the robot hand force, minus, in this case, kx. So k is the spring constant, x is the position, right? But the difference is, notice how, yeah, well, it's, I guess, similar to friction, right? So you take the Laplace transform and you calculate the transfer function, and you end up with something very similar to what we had before. In this case, it's 1 over m times s squared plus k over m, right? Now, you end up with a negative and a positive pole, right? Yeah, so plus or minus k over m I, right? So yeah, real part is 0, right? It's an imaginary number. The real part is 0. It's unstable. Now you might say, wait a second, but it would be stable. If I actually took a mass and I hung it from the ceiling, it wouldn't blow up to infinity, right? Right? Why wouldn't it? Well, because in reality, springs have a damping factor as well that you don't account for in that system. So it's not just the spring constant. You have this damping factor B. And the damping factor is what ends up making this stable, right? So the way you account for that is it's just another term. So the spring force is equivalent to how much I'm compressing or expanding, right? So if you expand the spring, it has a force that wants to bring it in, right? And if you compress the spring, it has a force that wants to bring it out, right? And that is a function just of how much you've compressed it, right? Which is x, the position, right? The position of the mass on the end of the spring, which is going to be the length of the spring, right? But the damping factor is a function of the velocity, right? Which is kind of like the coin. That's actually closer to what we had in the coin example with the friction. So anyway, if you go through this and you calculate the transfer function, you end up with poles that are both in the negative plane, right? Which means it's stable. Okay, and the other cool thing is that, I won't spend too much time on this, but the other cool thing about this is once you get this in a transfer function, you can actually calculate the natural frequency comes directly from this, this term here, this last term. So it's, you know, in this case, square root of k over m is the natural frequency. So you can calculate how the spring will, the frequency the spring will naturally bounce at. Okay, and then finally, you can do the same thing. This turns out to be equivalent to RLC circuits. You can do the same thing. I'll just run through this really quick. You can calculate the S-domain transfer function here and find the poles. And as it turns out, if you build a LC circuit without any resistance, it's also unstable, right? But of course, in reality, you always have a resistor in there. And so you end up getting poles that are in the the left-hand plane. Okay, and then the other cool thing, oh, I mentioned this too because in our lab, in this lab, we have a low-pass filter that is on the circuit board, right? I told you about that. So the input to, so we have a pulse width, a PWM wave signal. It's going into an amplifier, and the output of that amplifier is connected to a speaker. And we're going to try to get audio, right? That's your goal. The problem is that Alex found out the hard way that if you do that, you end up with these the PWM. You know, it's like a square wave. I mentioned the step function has an infinite number of frequencies in it, right? Now the PWM signal coming from the chip, the ESP32, is not a perfect square wave because it doesn't have an infinite slope. You know, a square wave has an infinite slope. You know, it goes from 0 to 1 instantly. It means it has an infinite slope. Coming out of the ESP32, it's not an infinite slope, but it's pretty steep, and it has a lot of frequency components in there. And some of those are high frequency components. So the way that manifested it is what did it do? It hurt your ears, right?
It's like a super high pitch, like what you would get from a CRT TV, except like much more painful on the ears.
Yeah.
I couldn't leave the thing running for more than like a minute. It's like really painful.
So he added a low pass filter, right? What is a low pass filter? Well, what's happening there is that's just an RC circuit. So we have the signal coming in from the ESP32 is a time domain signal. And I have VI VI, voltage in, right? And then this is voltage out, right? So this is the signal that's coming out of the filter going into the amplifier, right? And then into the speaker, right? Okay, so then you can calculate the, you can do the same kind of analysis here. You can convert this to, it took me a while, as you can see, to get here. But basically, I solved this circuit and I put it in the S domain, right? Assuming I did this right. And I'll skip over to the end, but basically the transfer function that you end up with, again, you have to convert everything to the S domain, then you have to calculate the transfer function, which is the V out over V in. Once you do that, you end up with a transfer function of 1 over 1 plus S RC. So I left the resistance and the capacitance, I left those as variables, right? So 1 over 1 plus SRC is the transfer function, okay? And it turns out that if you have a transfer function of 1 over SRC, or actually anything that's 1 over S plus, anything that's 1 over something times S plus 1 is a low-pass filter, is a passive low-pass filter with a cutoff frequency of whatever the coefficient of S is. Right? Now you might say, well, how do you know that? I don't know how that's derived. That's just a rule. It's one of those things where if you have a transfer function in this form, then you can take part of the equation, part of the transfer function, and that becomes some term. In this case, the term is the cutoff frequency. So the cutoff frequency is where any input sinusoid that's above the cutoff frequency will be attenuated by at least, I think it's 20 decibels, I think is the rule, something like that, right? Meaning that it will be greatly reduced in amplitude, right? So the cutoff frequency is, in this case, is 1 over RC, right? So I had to go back and figure out what Alex put in as the R and the C to figure out how to then calculate what that cutoff frequency is. Because he just chose those himself, and I don't know what the criteria is there, right?
I intended that to be about like 10 times that number, so I must have like accidentally made that resistor seems right, but maybe I accidentally got the capacitor off by like order of 10. I might have done it wrong because I just calculated this, but I came up with, so he's got a resistor that's 1.2 kilo ohms. He's got a capacitor that is 10 nanofarads, I believe. Yeah, let me
And if you take 1 over RC, you get a cutoff frequency of 1.3 kilohertz. Okay? So that's why when you do this lab, it's not going to pierce your ears, right? Because but maybe I might have calculated wrong. It turns out you can also build a high-pass filter, but we didn't do this. But a high-pass filter is when you just swap the capacitor out for an inductor, and you get a high-pass filter, except in this case, when you solve the transfer function, it turns out that it's S over S plus something, and that something is also the cutoff frequency. Now, oh, by the way, sorry, I should mention, whenever you find the frequencies in a transfer function, you get radians per second. In order to convert that to hertz, you have to divide by 2 pi, right? Divide or multiply? Divide. Divide by 2 pi, right? So anyway, in this case, if you design that with R and L, the high-pass filter is R over L. So it just passes high frequencies and it attenuates low frequencies. Okay, so that's all I've got for today. We'll continue this next time. I should be able to finish this up in the next lecture.